Good morning, everyone. I think we're going to get started. My name is Elena Jia. I have my colleague Jim Vanderwall here from the Fraser Basin Council. Thanks for joining us for our webinar this morning on using 3D modeling for Green Shores projects. As you can see on the screen, there's two different audio options. You can connect through your computer or through your phone line. And if you choose to through your phone line, it'll prompt you with the number and the access code. So this webinar is part of the BC Regional Adaptation Collaborative Series. And through the BC RAC program, we work to support local governments, First Nations, and private industries to incorporate climate change adaptation into their planning and decision making. One of the main resource portals we have is the retooling website. You can see the address there at retooling.ca. And when you visit that website, you can reach adaptation reports, guidelines, and toolkits on various different topics. You can sign up for our retooling newsletter to receive quarterly updates about different events and resources that are coming up. And some webinar logistics for today. So we're keeping everyone's audio muted just to limit the background noise. If you have any questions throughout the presentation, you can type them into the question box that you see in your control panel. We're going to save all questions until the end during our Q&A session. And if you're encountering any technical difficulties, you can also type those into the question box, or you can send an email to fraserbasin@gmail.com. And some upcoming events that you might be interested in. We have our next webinar on April 6th on the drought response in the Okanagan Valley and some of their lessons learned. So you'll see on your control panel that we have a handout attached, and you can download that for some more details about this webinar as well as the registration information. So today we are lucky to have two really great speakers with us. So the first is DG Blair, who's the Executive Director of the Stewardship Center for BC. And as the Executive Director, she's been at that organization since 2010. And their DG provides leadership and facilitation of collaborative stewardship initiatives with partners in government, industry, and NGOs. She's responsible for managing the Stewardship Center for BC's Green Shores, Species at Risk Primer, and Stewardship Practices demonstration projects. And DG also provides technical expertise in environmental issues, education, outreach, and evaluation for many of the center's projects. And our second speaker is Dr. Nathan Vadeboncoeur. And he's working hard to make science accessible to everyone by developing intuitive, interactive ways to visualize and interact with scientific and technical issues. He hopes to help increase public engagement in planning for a common future. And Nathan has worked with local governments, academia, and non-governmental organizations on flood and coastal risk issues across BC, and is the president of the not-for-profit Community Risk Network and founder of Smart Shores and its agricultural cousin, Smart Soil. So at this point, I'm going to pass the presentation over to Nathan. So if you could wait for a few seconds.
Good morning, everyone. Thank you to Fraser Basin Council and Jim Vanderwall for hosting this event, and to DG Blair and the Stewardship Council for inviting me to participate in this Smart Shores series of programs. Today, DG and I will be speaking about 3D modeling approaches for green shore projects, and before I get into my piece, DG is going to start to provide some background on the Green Shores program.
Okay, next, first slide there, Nathan. Perfect. Well, good morning, everybody. As Nathan mentioned, my name is DG Blair, and I just thought I would start by just giving a brief mention of the Stewardship Centre's mission. Basically, we are all about strengthening ecological stewardship across the province by providing educational, technical, and capacity programs. One of our key programs is the Green Shores program. This started back in 2003 when Coastal Shore Stewardship was published, and that ultimately led to the Green Shores program beginning in 2010. Basically, the idea was to move from general guidance material in coastal shore stewardship with some more specific design standards that were developed and moved on from 2010. Basically, Green Shores is based and created as a rigorous standard, which is based on these 4 guiding principles. The first is to preserve or restore physical processes, that is to say, the natural actions of water and sediment movement that maintains healthy shorelines. And when we do things like harden shorelines, that basically interrupts those natural processes. So we want to maintain or restore those physical processes, as well as maintaining or enhancing habitat function and diversity. The third principle is to prevent or reduce pollutants from entering the aquatic environment. So we not only pay attention with what happens on the interface between the, oh, can we backtrack there, Nathan, please?
Yeah, I think I just went on a timer.
Yeah. Okay, there we go. So, so we're not only concerned with that interface between the water and the land, we actually in Green Shores deal with the upland as well. So we minimize those pollutants from entering the aquatic environment. And finally, we want to avoid or reduce cumulative impacts, those small individual effects that can add up to large impacts. And especially you can see that when we deal with residential properties, because often on shorelines, we want to, the way that land use is developed over the years, we tend to maximize the number of homes along a shore, and those cumulative impacts can add up to some really big impacts. So we want to address those 4 guiding principles and all the design standards that have come out based on Green Shores. Okay, next slide, please. Basically, Green Shores is science-based. It promotes designs for shoreline projects that dissipate wave energy, accommodate storm surge, and lessen flooding. The design standard also is aimed to restore habitats, that shoreline ecology, that very important physical process in terms of sediment transport, as well as creating and maximize natural areas along the shores. Basically, it offers a resilient approach to sea level rise and climate change adaptation. If you look at the photographs on the bottom, we've got a hardened shoreline on the left-hand side, and in the same storm conditions, Green Shores, same storm conditions and a location nearby the hardened shoreline, and you can just see how that shoreline is way more resilient in absorbing that wave energy as it meets the shore, so you don't get those big impacts. Next slide, please. Green Shores is the overall program, and we have 2 credit and rating systems associated with it. The first one is Green Shores for Coastal Development, and that was created, as I mentioned, in 2010. And then Green Shores for Homes, which was released in December of 2015, and that is for residential properties. Next slide, please. So just talk a little bit about Green Shores for Homes. Basically, we are looking at residential properties. It's designed for both freshwater, lake, as well as marine shorelines. And the intention is to improve, to encourage incremental improvements. So that is to say, if we have a property and a shoreline project that for whatever reason they have a completely 100% hardened shore, and they need to, or we encourage them to take out as much of that hardened shoreline as possible, but we give them credit if they take out 80%. So we're trying to encourage that incremental improvement. In terms of the, moving on to the next slide, basically these application requirements are very much linked to the 4 guiding principles. And basically what we want is to have, from the residential perspective, things like an existing conditions plan, a site design plan, an environmental management plan, and that critical or sensitive habitat. And this is where there's a really strong link to smart shores and what we can, this information that we can gather. So there's a really great connection there. Moving on to the next slide. In terms of green shores for coastal development, this is a marine focus only at this point. It's applicable to parks, mixed-use residential, commercial, or institutions that happen to be along the shoreline. Again, it's based on the 4 Green Shores guiding principles. And generally the scope of Green Shores for Coastal Development is for larger scale projects. So as such, it has more requirement for professional sign-off on the design and the construction of these types of projects. Moving on to the next slide. We have what we call prerequisites rather than application requirements. We have 5 prerequisites. And again, you can see the connection to the 4 guiding principles. We want to have permanent structures moved away, site away from the actual shoreline. We want to conserve critical or sensitive habitats. We want to have a healthy, robust marine riparian zone. We want to conserve those sediment processes as they move along the shoreline and have an on-site environmental management plan. All certified projects must meet these 5 prerequisites in order to get the Green Shores rating. And I think one of the things that's different between the 2 is that on Green Shores for Coastal Development, the bar is quite high in terms of making sure that these 5 prerequisites are met prior to moving on. Okay, next slide, please. So basically, where we're going with this is we want to move projects, particularly as climate is changing and sea level rise is happening, from projects that move on the top. We get projects on the top level of your slide there with that rock hard armoring to more natural-based solutions. Like such as seen on the bottom, the photographs on the bottom of your slide. And in order to actually have really good design of these sorts of projects, having a very good understanding of what is actually happening on the shore, as well as visualizing different solutions, smart shores will really help with that. So with that, I'll turn it over to Nathan to carry on, and look forward to questions at the end if you have any. Okay, thanks.
Thank you very much, DG. Excuse me, I have a bit of a cold here, so I'm going to be coughing intermittently. So what Smart Shores is, as DG outlined, is a way of taking landscape data, like elevation data, and ortho images, the typical stuff we'd use in GIS applications, but making it something that could be accessible to everyone and interactive. So what we do is we take landscape data, build it into 3D models, add some images to make it photorealistic, and then we can animate different kinds of flood events, water level changes like sea level rise, landscape changes such as green shores programs, and see how these would look in an imagined or in a planned future. And so this image we're looking at right now is a photoshopped image of 5 different ones that illustrates broadly what the process of smart shores model construction is. If you can see my cursor on the screen here on the left, this is an image collected from a drone on the Sunshine Coast in British Columbia. We take these images, many overlapping images, get stereoscopic image pairs, and use that to create a point cloud. This point cloud will be integrated with GIS data to give it real-life landscape precision, so we know specifically where it is. This point cloud then gets built into a mesh. That's that gray piece just center right. And this mesh gets a texture built onto it by taking images, building UVs in the mesh, and reprojecting them. A UV in a mesh is just how you take a flat 2-dimensional image and change it slightly to fit a 3-dimensional shape. And so what we have on the right is a 3D model that is photorealistic and very similar in quality to the model on the left there, or the image on the left, which is just an image. So here in this picture, it started just a picture of this landscape, but I photoshopped in different stages of the process to show the visual fidelity that we can produce. Now, before I get into this a little bit more, I want to make sure that I'm able to tailor this talk to the interest of everyone who's listening. So we have several multiple choice questions that'll come up throughout the talk, and the first one I'd like to put to the audience now, if we can. So the first question, see if it comes up here. Which of the following are you interested in? Please select one or more of the following issues so I can get a sense for what it is your audience is interested in. Learning about flood risk visualization, using the data that we collect through smart shores for environmental monitoring and conservation, a more purely land survey approach, anyone interested in industrial applications, or in research applications. So we'll give you maybe another 10 seconds to make selections there, and then we'll have a look at the results. All right, could we close the poll, please? Thank you. All right, so flood risk and environmental monitoring conservation dominated. That's good. That's very much in line with our theme, with some interest in surveying and research, some in industrial, but mostly not. So I'll focus the discussion then on flood risk and conservation and the applications for that in research. All right, so we'll come back to our presentation here. So the smart shores concept came about because I felt there was an opportunity to help explain flood risks to people in a way that would help engage people a little bit more. I'd worked throughout graduate school on flood issues. I'd done flood research after I was finished there, and worked on a national coastal climate science assessment. And 2 questions kept coming up. One was, we need more data, and the second was, how do we communicate it once we have it? And we talked a lot about these numerical models that we had, and how can we get people to realize what the importance of even 25 centimeters of sea level rise is, because of the effect this has on sediment transport rates and the effect this has on wave attack on the shoreline. And so we thought maybe visual images could convey it. So I have here one image. This is sea level rise, sea level today, and the second image is sea level in the year 2100. So the sea level on its own isn't the data that we're interested in. What we're interested in really is relative impacts. And what are these impacts relative to? And they're relative to the landscapes and the areas where flooding will affect people. Disasters are largely by our own design, in that disasters such as a flood happen when things that people value get in the way. People's homes, people's communities, parks, infrastructure, neighborhoods, and the things people need for their livelihood and well-being get damaged by floods, and there's interruption to people's lives. And so how can we try and show what impact a more abstract numerical model like sea level rise and wave attack and storm models really means to a community. But getting beyond just this number, sea level rise is 20 centimeters, oh, that's bad. 50 centimeters, that's worse. A meter, that's even worse. But it doesn't matter unless it's relative. So what Smart Shores tries to do at the outset is take changes to landscapes, changes to sea levels or to wave or to erosion, and make this visible and in a way that people, that stakeholders will be able to recognize and identify, so that people can tie these global abstract issues like climate change and sea level rise to effects in their community. So this is what I started out doing in 2009, was trying to visualize floods. So what we did was we built 3D elevation models, really height maps in GIS, and just took a two-dimensional blue line that represents flooding and put that over top. This is research I did about 7 or 8 years ago in the Sunshine Coast. This is Davis Bay, and what this is a storm surge. This is a 10-year return period event with 1 meter sea level rise in the year 2100. So we can have a look down and see that there's a lot of flooding right around these coastal areas. Some homes are impacted, and that's good. That's a step towards engaging people, but it's not really enough, I think, to get people really interested. People who are already interested might see this and think that's nice. I understand the implications of this, but we wanted to try and go a little bit further. So we, over the years, myself and the people that became my team, through talking with different folks, sorted out, how can we try to sort out different ways to visualize these data. And then all of a sudden, drones became really cheap. We can get decent ones for maybe $2,000. Nicer ones with nice cameras are a lot more, up to 10 or 15,000. But still, relative to the airplane and jet fuel and pilots you need to fly aerial data, it's quite cheap. So it opened up an opportunity to explore different ways of collecting landscape data and visualizing floods and water and ecosystem changes relative to those data. So we started building a platform for visualizing different environmental changes in an interactive 3D model of a landscape. And I've talked a bit about work I did in the Sunshine Coast. I did that previously, and the Community Risk Network, with the support of the Institute for Catastrophic Loss Reduction and the Cooperators Insurance Company and some academic partners, are developing some flood modeling and storm surge forecasting tools there. But those projects are still underway. And what I'd like to profile today is an early adopter, the first adopter of Smart Shores, which is the Cowichan Valley Regional District. When I began working with them in the fall, Smart Shores wasn't Smart Shores. It was just taking 3D data, taking drone-based surveys, and communicating it in an improved visual way from the GIS-based application I showed previously. But as we were working with them, we kept developing our software, and I approached them and said, we're getting towards building, what is now Smart Shores. Do you want your data now, or do you want to wait and see how it goes? And they replied that they want something that's going to be high quality, that's more important than time, and they've been wonderful in working with us to together come up with a really nice big coastal model and lake model for nearly 300 kilometers of the shore and coastline of the regional district. So I'm going to see what we have here. This, if you want to take a look at an example of a model, feel free to take out your smartphones and have a look at the QR code here. If you don't have a smartphone with you or a QR reader, there's a link next to it you can go to see a model. And if you don't want to do either of those things, I'll pull the model up in just a minute. And just so I have an idea of who's using what here, I've got a second survey question. If we could put it up, please. So is anyone looking at the 3D model on their phone, or trying to look at the 3D model on their phone? I give about another 10 or 15 seconds to get that together. and then I'll have an idea of how good of an idea QR codes are for communicating online-based data. All right. Hey, some people are on the phone. That's great. Most people are not. So I will get this up right here. So what the QR code linked to was this. This is a little snippet of a 3D model we built along the coast of Mill Bay. So this is Brentwood College. And so what we can see here is some of the shoreline features, and the models can get quite accurate. We can see not just general elevation of the land on a slope, we can see individual rocks, and we can see, to a less extent, bushes and trees. The process of photogrammetry, which is where we take stereoscopic image pairs and build those into a 3D model, doesn't get along with trees and bushes very well because they have leaves and the leaves blow, and so the model has changing goalposts. And so we can see here we've got we're doing a little bit better than we were with the GIS based data. We now have a landscape that people can really recognize. It's not just a top-down two-dimensional thing with water. We have a landscape, but this landscape on its own isn't enough. We want to be able to add more things to it. We want to be able to add animations. And so what we've done is we've developed or almost finished our first build of a software program that allows us to navigate and fly through landscapes and look at different flood levels. Now, just before we get to that, for those who are interested, I'll show a brief video of how we build a model like this. So we'll start with a series of images. Align all these images together by matching pixel to pixel. And that'll generate a sparse point cloud, which is what we see here. This is the Cowichan Estuary with the Quicksila River here, and one of the arms of the Cowichan there. And so this sparse cloud forms the basis of the model. We then integrate our GIS data into it and calibrate it so that it fits, represents the real world. After we've done our sparse model, I'll use one chunk here just for the purposes of computational ease, because we're going to get into some pretty data-heavy things. We take the sparse point cloud and then, with using those tie points, create a dense point cloud. So this is a very dense cloud. Looks fairly realistic here. It's a little over 1,000 points per square meter, compared to LiDAR, which is usually about 150, 170 points per 10 by 10 meters. So it's substantially more data intensive. We then build, as you saw in the last image, a polygonal mesh, smooth the mesh, colorize it, and then what we'll see here is add a texture by reapplying image textures with UVs to the landscape. So the advantage of this over GIS is really the interactivity. And this is not our software. This is just the software we use to develop the program. We'll see the software in a minute. But we can change views and look at obliques of a landscape. And so without having to get into GIS, having specialized software and specialized toolkits, the software we've developed that we put these models into allows anybody to go and explore what looks from the top, like vertical elevation data and orthophotos, but look at it from an angle that people would be familiar with if they were walking on the ground and actually experiencing an environment. So there's a few things we can do with this. We can create digital elevation models, colorized here with the reds being the highest to the yellows to the blues. We can create orthophotos, and we can use measuring tools to identify and measure the length of certain objects. Here's a 13.3 meter log. We can calculate the volume and volume change of landscapes as well. So that's the process behind what we did here. There's one other QR code I'll put up for those who are interested. Get your phones if you'd like to interact with it yourself. It's nice to have that tactile thing where you have a model. It's not just viewing, it's the controlling and manipulating it on your own, and I find pretty nice. So here's the second one for those who'd like to get their phones out and try the QR codes. For those who are just pivoting, one finger, yeah, you pivot the model. 2 fingers, you drag to change your perspective and change the point in which the model pivots. So in 5 seconds, I'll go back out of this slide and show the second model. All right. So the second model is an example of a log jam in Cowichan Lake. So just like for Brentwood Bay, we're able to reconstruct a landscape. And why I wanted to show this, in addition to Brentwood Bay, is Brentwood Bay has got some really easily recognizable features, buildings, and the like. And this is much more purely ecological. And I wanted to show this as an example of the level of detail that we can produce. This particular model is, I think, 3 centimeter internal model accuracy. So that means every 3 centimeters gives us one little polygon, so we can measure things to that level of accuracy. So we could measure, for example, the volume of wood floating above the water level, and get an estimate for what the weight of this wood is, and how much, if we want to clean up the log jam, about how much effort that would take. So what do we do now that we have these models? We've been able to develop them, but the next thing is making them interactive and making them the kind of things that people are going to want to interact and play with. So we're working on developing a video game that, as I mentioned, is almost ready. That's going to allow people to look at landscapes, add some animations, interact with different dialog boxes, for example, clicking on the logjam and learning what the volume of wood is, for example, or learning about how it occurred, learning about the history of timber in the region, whatever kind of value-added information someone would like to incorporate. So I'm going to show is 2 things here. The first is our initial prototype. We're going to go back to the Brentwood Bay example. It's going to look a little bit post-apocalyptic, but that's okay. It was early stage. It's better now. And that's the little EXE that I'll fly around to show you some of the interactivity of the game. And the second is I'll show you a video of where we are now with our near finished product. And that'll be an example of Shawnigan Lake. So our game looks like this. Hopefully this streams well. It's pretty data heavy, but hopefully it just comes across the wire as video, and it's all good. All right, so we've got a little bit of audio here. There's a little bit of waves we can hear. There's a seagull. So what we can do is fly around. And the reason here that we have these post-apocalyptic looking buildings is we're doing a shoreline model, and the buildings were just context for background. So we're kind of in the periphery of the data we were collecting. If we wanted the buildings to be really sharp and crisp, we could do that, but and I think we will in the future because we want better-looking buildings. They are a little bit better looking now, but you know, they've got to be better than they are here. So you can see for the shoreline here, the resolution is pretty good. And what we can do that makes this interactive piece nice, let's come down a little bit here, is we can play with different water levels. So let's say we wanted to see low tide. We can bring the water down and see what low tide looks like. We can bring it up and see what high tide looks like. We can animate waves to show what those would look like. We can add sea level rise. Sea level rise plus waves. If we really want to freak people out, boom, we can go and make the water unrealistically high, but we don't really want to do that, so we'll probably keep it based, science-based. So what this game allows us to do is fly through a landscape and play with different ecological parameters. So we could change water levels, waves. We could even take out this building that forms part of Brentwood College and build in a different one if we wanted to look at what a potential future might look like. If we wanted to change this riprap along the water, these rocks. We could build in different rocks. If we want to take them out and create a more natural or maybe more vegetated shoreline, we could do that. So we can explore different options for future shorelines. And so you can see here, this is just the chunk in space as water goes on forever to the horizon. So it leaves something to be desired. So what we've done is we've then expanded our build a little bit. And here's a little fly-through of what we have. It's a screenshot, so it's a little lower res. I'll show you a higher res image in a minute. I'll just play this little video to take you on a little tour of Shawnigan Lake with some background integration. So here we have a really low res background, texture. What we're working on now is getting a background texture resolution that'll be 100 times better, and the geometry will be 90 times better. So when this final build is complete, instead of having the model just kind of popping up next to a flat and pixelated shoreline, we'll have much better geometry. So we have a lot better, the shoreline model looks like it's a part of a virtual world. It's a little more seamlessly integrated. Now, as a kid, I always liked trees. You know, I'd hang out under trees and enjoy their shade in the hot summer. But as someone doing photogrammetry projects, I don't like trees so much because, as you can see, Shawnigan Lake is full of trees. And these things are really hard to model. And after lots of work, they still kind of look like blobs, like that. So what we're going to do, let's see if we can go back to the blob. We're exploring ways to just take out the trees and put in video game trees. So they'd be kind of, they'd be realistic-looking trees. They could blow in the wind. They could do different things, and they wouldn't just be these blobs. But it's quite a lot of work to develop software. So we're going one step at a time, and we have to make sure that everything works really well, because with all the high-quality apps and programs out there, people expect things to work great right away. If a user's got a bad experience in the first 30 seconds, they're going to go, you know, Smart Chores is no good. I don't want to use it. You know, so we have to make sure our interface works, everything's good, and then we can go on some more cosmetic changes. So here with the background, we got a much nicer looking model. We flew along the water here. We can fly in the air. We're going to work on developing a little virtual boat people can go in that has water physics, so you can drive it as you would a boat. And let's see. Oh yeah. So now we have that. Here's a higher res image of what our Shawnigan Lake model looks like. We did Shawnigan Lake first because we have about 140 kilometers of coastline, a little over 100 kilometers of Cowichan Lake, and then some rivers. And Shawnigan Lake was 27 kilometers. So we thought it'd be the easiest for a first build, but it also is far and away the most treed. So we've been working that out, and now we have what you see here for Shawnigan Lake. Water levels will move a little bit because there's no big tides or sea level rise, but we'll be able to explore nonetheless different water levels. So coming out of that 3D virtual world there, I'd like to get into a question of the roles and responsibilities people have in mitigating hazards and the kind of tools that Smart Chores provides for doing that. I'll go through this. It won't take that long, and we'll get into our questions. So since there's a lot of talk about what different levels in the flood world of government should be involved. Local governments were involved for designating floodplains. The provincial government, who provides some funding and gives them that authority and has some disaster management responsibilities, and the federal government, who also has disaster management responsibilities and provides some data. But I've not heard anywhere near as much the discussions about the kind of responsibilities that we as citizens have for our own communities. People talk often about climate change as a global issue and think, let's write to the Prime Minister, let's write to maybe the former President of the United States and try and work out ways to get treaties signed, get emissions reduced. But those are really big scale targets. It's hard to really engage effectively as small groups. But what we have in Canada, and especially in British Columbia, is a lot of power that local governments have. And if individual people go to local governments who control zoning, who control floodplain designation, there's a lot of change that I think can happen at a local level. And by giving people a visual tool that allows them to better understand and engage with coastal science and coastal risks, it gives people more a more knowledgeable basis for engaging in these discussions, and maybe helps motivate more talk around what we can do collectively for flood management in BC. So to support local governments in planning for floods, there's several tools that we produce as well in terms of data outputs, not just 3D visualizations. One is digital elevation models. This is one of the logjam. These can be typically about 3 centimeter precision, just given the limitations in GPS precision. We use a Trimble R10, which is capable of sub-centimeter readings if the satellite constellations all work out well and we've got nice north-facing exposure. Then when we integrate that into a photogrammetric data set, the accuracy is usually double. So say you get 1 or 1.5 centimeter precision, that means you're looking at 2 to 3 centimeter precision in a model. We can make orthophotos based on the DEM. We can do multispectral imaging. This is of a farm with some elevation contours. We can see this crop here in the bottom. It doesn't look nearly as vacant there when we don't use a multispectral image. We can see here there's a bit of a depression that suits this, making the soil a little bit more humid and a little bit more charged with everything, from nutrients to pesticides, that those plants didn't like so much. We can do volume calculations for looking at shoreline change. And with our DEMs here, this is one of the better examples. This internal accuracy is just over 1 centimeter. We can see on the level of tire tracks from vehicles that drove through the landscape. And to come back to how we use these data to inform discussions, as I see, so when we're dealing with climate change, and all hazards really, 3 general categories of risks. There's the daily risks, things we see every day, like tides, atmospheric pressure changes that can affect water levels. Don't see those very much, but they happen. We're at least aware of the minor water level changes that are caused by them, and wind. We see this every day. Everybody knows about it, and you'd be crazy to build a house below the high tide mark because you're going to get flooded. So no one would do it because that's a really salient hazard. There's seasonal and annual variation. There's changes to circulation. There's El Nino. These things happen, within years to several years. We're ready for that as well because we see it. It's a regular enough thing. But when we get up to the decadal scale, this is like the Pacific Decadal Oscillation, which is about a 30-year cycle. Glacial mass changes that affect the height of the tides. Things like sea level rise of decadal or even 100-year plus timelines. These are things that aren't in our living memory, aren't in our institutional memory, and things that we're not really planned for. Sea levels always fluctuate. Land levels relative to the sea always fluctuate. This has happened for tens of thousands and millions of years, and will continue to happen. But we don't plan for it because we've been only alive for several decades. Vancouver's only been a city for people a developed city with hard infrastructure for maybe 150 years. So these things that happen on really large timescales we're not aware of. So if we can collect data that allows us to monitor little changes to prepare for things like storms, and so PDO through the data that are available here, but also provide visualization so people can understand better future scenarios and bring those into the planning discussion as well. That's something that we really want to try and produce through smart charts by allowing people to imagine and engage with different futures. So our driving question is, how can we explore hazards so that we may better prepare? How can we provide affordable, high-quality data to local governments who are responsible for dealing with these floods in British Columbia? And how can we take those data and the findings that we produce from analyzing them and bring that into the public discussion so that we may all together engage in planning for a common future? That's my presentation. DG and I's contact is here. Thank you very much for attending. We'll get to questions in just a sec. But before we get there, I have a couple more questions for you. Would you please put up question 3? And we'll just go about 15 seconds of questions, so we can get through these quickly and get to answering questions verbally. So please select each data format you would find useful. That is, if you find these the things covered by the presentation useful, what are you interested in? One or more of the following: survey data like DMs and orthos, just purely visual data. Do you just want to see what shorelines look like and doesn't matter where they are in physical space? Are you interested in interactive scenarios and communication tools such as a video game? Or would you be interested in going down the multispectral data route? That's for things like ecosystem classification, vegetation and plant health indexes, things like that. One of the tools that we have through Smart Tours that I didn't speak of much was that by reconstructing these photorealistic 3D landscapes and producing orthophotos quite quickly and easily, we can look at ecosystem change at a very fine scale, up to even sub-centimeter level pixels when it comes to just looking at ortho images. So there's a big ecological classification opportunity there. Okay, so the multispectral, yeah, it's not the sexiest thing. Okay, interactive scenarios. Okay, there's some use there, but mostly the visual data and the survey data. Okay, great. Thank you. Could we go to question number 4, please? How likely would you be to use complementary software for stakeholder engagement regarding environmental risks shown by 3D models? So this needs just a little bit of explanation. We're thinking of developing an online platform that would accompany the video game, that would allow people to click on different info boxes in the video game, explore scenarios, learn about different features, and interact through a kind of online consultative process so that we can help draw everyone in to these local discussions. For example, I'm in my early 30s, I've got a couple kids, I've got a business, I'm working hard, I don't have much time, I can't get out to community meetings, but I would like to participate. So we're trying to create an online way of engaging so that people who are either away or are unable to make it, especially younger people who don't participate as much, can get a little bit more involved. So that's what this question is about. How likely would you use it? Okay, good. So I'm glad to see there's some value there. Great. Thank you very much. And there's one last quick question. I've broken my 15-second limit, so we'll leave it to this one, which is pretty short. What do you think of those photogrammetric trees, those blobs? Are they tremendous? Are those pines fine? Would you prefer better-looking trees? Oh, wood. It was supposed to be W-O-O-D, but that's okay. Too many dad jokes and puns. Or is it just total bush league? So how bad are those trees? How badly do we need to change those? All right, everyone should have their opinions in. What are the results? Yeah, they're pretty bush league. Prefer better-looking. That's good. Whoa, some people think they're tremendous, or maybe they're just voting for the phrasing. Either way, I like it. But yeah, that's good to hear. We're looking at making those trees a little better. So thank you very much for listening to me, and now I'm happy to take any questions that you may have.
Okay, well, thank you so much, Nathan and DG, for your presentation. It's really neat to see those models and the videos, so thanks for sharing those. So right now, if people have any questions for either presenters, you can type them into the question box. And the first one we have is for DG, referring to an event that this person had attended last Friday at the Green Shores workshop at UVic. And this audience member wants to know the information on the Green Shores for First Nations that's happening in Vancouver.
Right, and that's thank you for the question, and that is on March 21st and 22nd, and I will offline send that specific contact information to them. And my apologies for not getting to that just yet, but I will send it. And I think for others who may be interested, there is a 2-day meeting that's being hosted by don't have the actual information, the full information here, but it is focused on First Nations and adaptation. So they can get in touch with me at my email address, and I can forward that information to them.
All right, perfect. Thank you. So our next comment and question. Drones are wonderful for their high spatial resolution, but have you been able to build time series to analyze trends over time? How is the stitching?
Stitching images over time. So what we've done one field seasons, that was last summer, and now we're working on going back and collecting more as soon as the snow stops. I'm looking outside; it's still snowing. The one thing about drones is they're basically flying pieces of electronics, so they don't do so well in inclement weather. And so what we're doing is going to collect multi-year time series data, and to compare that, we'll use a software like Cloud Compare, where we'll take the dense point clouds generated by the photogrammetric process, and we'll be able to compare changes over time. And we could animate those into a model, or we could just take, or rather animate them into the video game, or take a more data approach and just have someone just kind of manually click through different years and look at how different say beach volumes changed among erosion and things like that.
Okay, thanks, Nathan. And another question regarding cost. So what would be the approximate cost per meter of shoreline to build a full model?
It depends what's needed. We're probably looking at between, I mean, if someone just wants a shoreline model, it might be, and if they're doing more volume, it'd be less than $200 a kilometer. It might be $250 with some to $300 with some GPS integration, and for full kind of full-on video game customized stuff, it might be around the $500 per kilometer range. But again, it depends on the project. If someone wants a survey on a place that's with easy accessible beach, we can park our car, get out and walk and survey. If someone wants to survey like bluffs and cliffs, that makes it obviously a lot more difficult for us, so it would put the cost up a little bit.
And another question is, when can people expect to be able to start using the Smart Shore software? Is it readily available right now?
It's almost ready. We're going to deliver within the next week or so our Shannon Lake model to the Cowichan Valley Regional District, and shortly thereafter we'll follow the rest of their models. We'll then do some for the Central Coast as well, and for a couple of estuaries. And after that, once we've ironed out our first full complete build, it would be available for people to interact with once the people who have requested decide that they'd like it to be public, and if anyone else would like their own, it would be ready for the public as soon as it's ready for them. So I guess a more direct answer is this spring and summer we'll be able to build models for people who would like them.
Okay, our next question, Jim Vanderwall here, is for modeling, why develop custom software and not just use ESRI City Engine, which can model trees and water, and what are the benefits of custom software?
Yeah, that's a good, expensive question. The reason for using custom software is it allows us to create something where we can control the interactivity, the animations, and the resolution, and also go in and use our own techniques for building different features based on photogrammetry. So if we want to be able to quickly take out a building, put in a new one, and have these animations work in a kind of like an easily accessible application, that especially one that would be free to interact with for any stakeholders, that's one of the advantages of the main advantage really of doing it ourselves. We could also integrate some value-added components such as info boxes, videos, things like that, and allow people with just a computer to be able to visualize it without having to look at videos or that were pre-produced fly-throughs, or have any of the Esri suite of tools.
Okay, great. what role will the new NASA hyperspectral cameras have in enhancing the data you can use in your models?
Yeah, those cameras are great. With those kinds of data sets and with satellite data in general, it allows us to do models at a lower resolution than ones collected by drones flying a lot closer to the ground, but still at at quite significant resolution, as people who have got the new version of Google Earth with the photogrammetric integration there can see. So we can take big landscapes and look at things like sea ice change. We can look at things like forest health change, climate change impacts on forests by looking at multispectral band images. So we can get beyond doing these kind of small sites and coastal bands to really doing large tracts of land.
Great. Question, is this Unity? Can you talk more about tree replacement and integrating background terrain?
Yeah, it is. Yes, it is Unity. And so for tree replacement, what we do is we would build. So first step is for each section of coast, we had to break it out into about 250-meter scenes. And for each scene, we use about 60,000 polygons. So with the trees, what we do is we'd remove them from the dense cloud and build a higher resolution coast. And then we would just use trees either from the Unity asset suite or design our own trees if we want to be really specific, and just virtually plant those along the bottom of the mesh. And for integrating with background, what we did in the model you saw was use USGS data, which is 30-meter resolution, which isn't really enough because it doesn't match the shoreline specifically. So what we've done that we've processed now and are working on integrating for our final build is we've taken 1 meter DEM data, LiDAR-based data that the Cowichan Valley Region District has provided, and this matches the shoreline model and gives us more background geometry. So it's not just flat; it gives us a much higher resolution texture. So we take height maps that are derived from the LiDAR data, turn those into a 3D mesh, and then use orthophotos. We convert the orthophotos to PNG and use those to apply textures. So we get a higher resolution background texture. So it's not just kind of colorful blobs like we saw in the background. It'll be recognizable landscape features.
Okay, great. And we probably have time for one or two more questions. It's been great to see all the questions coming in. What we'll do is any that we can't get to, we'll forward to our speakers, to Nathan and DG, and make sure that they have a chance to follow up with you separately. Another question is for Nathan, I guess, is have you had much success with integrating bathymetry into the 3D models?
We're working on that for Cowichan Lake, so that will be the first example of bathymetry integration. For Shawnigan Lake, we're doing some really basic bathymetry, but short answer is yes. Just like we build a background above water texture, we can build a bathymetric texture. So what we would be able to do is lower water levels, so we could see what an empty lake would look like. The difference there is we don't have textures, and the bathymetric data is usually more coarse. So we'd have a lot of contours, and you wouldn't really be able to, you just see kind of a contoured landscape rather than what it actually looks like underwater. But yes, we can integrate and are working presently on integrating bathymetry where available.
Okay, great. Well, I think we're just going to have to cut off questions there. And as I said, we'll have our speakers follow up with other folks directly on their questions. It's great to see the level of interest in this topic and in Nathan's presentation. Some really great tools being developed. I wanted to also mention that a recording of this webinar will be online in the next week or so. So you can check that out on our YouTube channel or link to retooling.ca. As well, there was a request here for contact information for our speakers, and we'll certainly share that in the follow-up. So I'd like to thank you all. Thank our speakers, DG Blair and Nathan Vadeboncoeur, for their great presentation. Also thank our financial supporters for our webinar series, Natural Resources Canada and BC Ministry of Environment. And so thank you all, and hope you have a great rest of your day. And look forward to some of you participating in our next webinar, which Elena mentioned, coming up at the beginning of April on drought management. So thanks everyone, and have a great day.
Okay.